Okay, these are notes 2.5, regression lines. Some of this will be familiar and some not as much. We're going to make predictions using regression lines, keeping in mind extrapolation, that you're going to be very familiar with. Calculate and interpret a residual, which is going to be new to you, and interpret the slope and the y-intercept of a line. That should also be pretty familiar with you. Okay, so when we look at a regression line, the line of best fit, we're thinking about that y is equal to mx plus b. That you remember back in pre-algebra and algebra 1. That m is our slope of the line, how much it goes up and over. The b is our y-intercept, where it crosses our y. Okay. Now, the textbook offers this one as well. So first, this part, notice they use a and b instead of m and b, whatever. But your slope is always what's next to your x, and your y-intercept is your other. Okay? Now, what they do is they use this hat. It's called y hat, and that means it's the predicted value. So that's a new notation for you from what you've done back in Algebra 1. So basically meaning this. So if I have a bunch of points, my line of best fit is what's my predicted value, my average. So if I wanted to know for like x of 2 here, okay, I could go up to the line and I could go over and I could see that my y is like a 3. So if I make a prediction with 2, my output would be a 3 there. Okay, my predicted value would be 3. Now, I have other points here that are above and below that, and we'll talk more about residuals here in a little bit about that. Okay? So, making a prediction. So, cars and trucks lose value the more you drive them. We can predict the price of a Ford F-150 if we know how many miles is on the odometer. A random sample of 16 Ford 150 Super Crew 4x4s were selected among those listed on autotrader.com. The number of miles driven and the price were recorded. Okay, so here's this. So notice the more miles a truck has, the cheaper it is, right? Because it's probably not going to last as long. So using this, okay, I think you know in Desmos, if you were just given, say you were just given the numbers in a chart, right, with x's and y's, you know you would use y1 tilde m x1 plus b, and that would give you what your slope and your y-intercept are. Okay, you've done that many times. So what they're doing here is they're giving the equation. Okay, so here's the equation, and they're asking you to predict the cost if there's 100,000 miles on the vehicle. So 100,000 miles, we could estimate it from the graph here. So 100,000 miles should be somewhere around $20,000 or so. Okay. But we can be more accurate by using the equation here. So we put that 100,000 miles in for the x. That's my x variable. Okay, so we put that in for the x, and you work that out, and my predicted cost is $21,967. Okay, so we have that making prediction. Now, let's say I want to make a prediction for something with 300,000 miles on it. So I could take that 300,000 and plug it into the x there, and it would equal negative 10,613. So, that doesn't quite make sense, does it? I'm not gonna pay negative $10,000 for this vehicle, right? They're not gonna pay me $10,000 for this vehicle. So this is an example of extrapolation. Extrapolation means that if my data is only between 0 and 150,000 miles, I don't want to make predictions for too far outside of there. If I make predictions for way outside of this data range, they're not going to be reliable. Okay? Like this one, it didn't make any sense. So we only want to make predictions that are close to the data that we're at. Okay? Too far outside and they're not going to be accurate for us. That's the idea of extrapolation. Okay, the second one is residuals. Okay? So with residual, I want you to think actual minus predicted. So I want you to write this down. A residual is equal to the actual minus the predicted. Okay? Actual minus predicted. That's how we find our residual. So for each individual point, we can find our actual and our predicted. Okay? So take for example, this point right here is so on this graph, we have this point right here, which is a vehicle with 70,583 miles on it, and it has a cost of $21,994. Okay, that's that point right there. That's the actual. Okay, that's the actual price. Now, to find our predicted price, so our predicted would be what's on our line here, right? Okay, so our predicted, we can use that equation that we had earlier and make a prediction for that many miles. So when we make that prediction, we plug that in there, and we get a predicted of $26,759. That's on the line. Okay, on the line is our predicted. Now our actual, they said, was $21,994. So to find the residual, what I do is I subtract those two numbers. If I subtract those two numbers, I get negative $4,765. Okay? Now, there's a negative and there's a positive residual. A negative, this point has a negative residual because it's below the line of best fit. This point here would have a positive residual because it's above the, okay? So our actual point here, okay, cost was more than what the predicted cost was. So you would have a positive residual for that one. Okay? So that's how you find the residual. Actual minus predicted. Okay? So let's do an example of another problem. Don't you hate it when you open a can of soda and some of the contents spray out of the can? And hopefully all over you, not over you. Two students wanted to investigate if tapping on a can of soda would reduce the amount of soda expelled after the can had been shaken. So my wife does that too. She goes like that on the top just to make sure. For their experiment, they vigorously shook 40 cans of soda and randomly assigned each can to be tapped either 0 seconds, or 4 seconds, or for 8 seconds, or for 12 seconds. Then, after opening the can, they cleaning up the mess, the students measured the amount of soda left in the can. And here's a scatter plot. Okay, so there were varying amounts left in the can. Okay, so the line of best fit here gives us the equation y is equal to, or y hat predicted. I'm going to write this a different way, just so that it's the way you usually see it. 2.63x plus 248.6. Okay, slope, y-intercept. Okay. So note that fewer than 40 points appear in the scatter because some cans had the exact x and y values. Okay, so anyway, we have the value there. So we want to calculate a residual. Tapping on it for something for 4 seconds, it had an actual of 260. Okay, so 260 would be about that point right there. So that point is just a tad bit, it looks like just a tad bit above this line. So would it be a positive or negative residual? If it's above, it's going to be a positive residual. Okay, just a little bit here though. Okay, so let's actually figure this out. So our residual is equal to our actual minus our predicted. Okay, now it said here the actual, okay, what actually happened for a 4-second can, for tapping on it for 4 seconds, there was that much remaining. So that's my actual, 260. And the way I find my predicted is I have to plug the 4 into this. So if I plug a 4 in here, it gives me 259.12. Okay, so the residual of our actual minus predicted is 0.88, which means we were off. Our prediction was off, was a little bit above by 0.88 milliliters. Okay, now interpret it. Okay, so the can had 0.88 milliliters more soda than we were predicting, than what we were expecting. Okay, so I want you to look at this. Which of these points do you think has the biggest residual? Okay, I'd say the biggest residual would be this point right here. It's the farthest away from our line of best fit. Okay, This probably is the second biggest residual. Maybe that's the third there. Okay, so residual is basically our error. How much error was there? When we make a prediction, how much error did we have in making the prediction? Okay. Next, we're going to interpret the slope and our y-intercept. We want to interpret those things. So if you think about slope, it was our rise over our run, and then our y-intercept is when the x is 0. Okay. So if we think about that Ford F-150, we had y hat is equal to 38,257 minus 0.1629x. Okay. So this part is our slope, and this part is our y-intercept. You could flip it around if you wanted to. Now, for slope, we want to interpret this. This as a fraction is that over 1. Okay? So, and this is the change in y over the change in x. Okay? Now our y, if you remember back on the problem there with the, remember the y was our price and the x was our miles. Okay? So this was the price divided by miles. Okay? So we could say, we predict, because it's a prediction, that for every mile driven, the price would increase or decrease. Okay, since negative, it's decrease by $0.1629. So about 16 cents. So for every mile that's put on a vehicle, it's dropping about 16 cents for every mile. Okay, so that's the slope part. Now for the y-intercept, our y-intercept was 38,257. Okay, so if you think about this here, our y-intercept is 32, whatever I said there. Now what's my x at that point? My x is a 0. Okay, so the interpretation of this would be at 0 miles driven, we predict the cost to be $38,257. Okay, so that's an interpretation for the slope and an interpretation for the y-intercept. Okay, a lot of times, and it depends on the problem, but a lot of times this y-intercept will make no sense. Okay, when there's 0, but in this case it makes a little bit of sense. Okay, so tapping on the cans. So we had the problem about tapping on the cans. We had this equation here. Y hat predicted is equal to 248.6 plus 263x. Okay, so interpret the slope. So interpret the slope. We think slope is this over 1, right? And in this case, if you remember, our y was the amount of soda remaining, x was the tapping in seconds. Okay, so slope is the change in y, which is the soda remaining, divided by the change in x, which was the taps in seconds. Okay, so we would say for every 1 second of tapping, we predict the amount of soda to increase by 2.63 milliliters. Okay? So for every second you tap on something, we predict that there's going to be that much more soda in there. Okay? Okay, so for B, does the value of the y-intercept have any meaning? Okay, so the y-intercept would be this. It would say after seconds tapping, we predict the can to have 248.6 milliliters in it. Okay, now, does that make sense for this problem? Okay. It has some meaning because it is possible to tap the can for 0 seconds, and it's basically telling us that there's how much soda is left. Like, if you don't tap at all, that's how much soda you would expect to have. So it does have some meaning here. But there, like I said, there's not always going to have a meaning. For example, if I had like student height and student weight, okay, probably have some sort of positive slope. As somebody is taller, they weigh more, okay? But would the y-intercept make any sense here? No, because we're not going to talk about somebody being 0 height. Somebody's 0 height makes no sense at all. So the y-intercept would make no sense there. It doesn't really work. Okay, so a little bit of a question here. Does adding sugar to the water in a vase help flowers stay fresh? I never really added sugar to flowers, but anyway. To find out, 2 students went to a shop and randomly selected 12 carnations. When they got home, they had 12 identical vases, and they put the same amount of water in everything. They put one tablespoon of sugar in 3 of the vases, 2 tablespoons in 3 vases, 3 tablespoons in 3 vases, and no sugar in 3 other vases. Okay, so no sugar, 1, 2, or 3 tablespoons. And then they put the carnations in and see how long the freshness. They had some sort of scale to do the freshness. And this is what they came up with. Okay, so what I'd like you to do is to use this equation here. And calculate and interpret the residual. Okay, pause it and do that. Okay, the residual is equal to the actual minus the predicted. Okay, so something with 2 tablespoons and 204 hours, that's what's actually happened. So our actual is 204. And the predicted amount, I have to take that 2 tablespoons and plug it in here. 180.8 plus 15.8 times 2. Get my calculator here. So 180.8 plus 15.8 times 2 gives me 212.4. So my actual is actually lower than my predicted, right? And I can look that here at 2 tablespoons, and the actual is 204, would be down here, right? So this point has a negative residual. So 204 minus 212.4 gives me a residual of negative 8.4. Hopefully you got that. Okay. Number 2, interpret the slope and y-intercept. So for our slope is 15.8, that's over 1. And remember, that is the change in y, which is the freshness, divided by the change in x, which is the sugar. Okay, so we would say for every 1 tablespoon of sugar, we predict the freshness to increase, because it's positive, by 15.8 hours. Okay, so that's the slope and the interpretation of the slope. Okay, number 3, oh, it says y-intercept. So the y-intercept is 180.8, which means we would say we predict for 0 tablespoons the freshness to last 180.8 hours. Okay, number 3, would you want to make this regression line for something that receives 10 tablespoons? So we only did up to 3. Do you think that if I add more sugar up to like 10 tablespoons, it's going to keep going up, up, and up? We don't really know. Maybe it does, maybe it doesn't, but it's too far to tell. Okay, so we'll say it's too far to be reliable. And that's called extrapolation. It's too far out there to go. Okay, so we talked about making predictions. We talked about the residual, how to find that. We talked about slope and y-intercept. Okay.